Dr. P.M. Bhargava.
Science is more than a sum of physics, chemistry, biology or mathematics. It is more than learning how to increase agricultural or industrial production. It is a question of ideas, a way of thinking. It involves observation and insight, reasoning and intuition, systematic work and creative impulse. Science gives us a culture and a philosophy of life which leads to pursuit of truth without bias or prejudgment. What then is the method by which science gathers knowledge and interprets it? It is important to grasp this method because it finds applications in many fields and often in resolving personal dilemmas. This exhibition is meant for 17-year-olds and above and tries to say something about the method that science uses to arrive at answers to questions. We hope that this method will also help you to find answers to your questions.
An introduction to the method of science. What method does science use to acquire knowledge? What are the characteristics of this method and of the information acquired through it? How would you verify whether or not a statement, a conclusion, or a piece of information is correct? What are your obligations if you accept the method of science and the knowledge acquired through it? This exhibition is intended to help you answer these questions. Let us look at some statements. By definition, a statement is either true or false, or its truth value is not known today. We will therefore also state what is, in our opinion, the truth value of the statement. Some objects can travel faster than light. We do not yet know whether the statement is true or false. It is a bad omen if a black cat crosses your path. This statement, we believe, is false. The sun rises in the west and sets in the east. This statement is also false. There is life out in space. Again, we do not yet know whether the statement is true or false. Similarly, the statements, "If you sow sonora wheat, you shall reap sonora wheat," and "Water can be made from hydrogen and oxygen," are true. The statements, "Atoms are unbreakable," and "Family planning cannot solve any problem," are false. If your opinion about the value of the statements we have made tallies with ours, the chances are that you have used the method of science, perhaps without being aware of it. The method of science. What is the method of science? This unit describes the 4 steps used in the method of science and gives some examples of its application. However, before we go any further, it is important that we are clear about certain definitions. Firstly, in science, we define truth as an answer arrived at by using the method of science. Such truths have several special attributes. For example, they are not absolute or unchangeable. Secondly, we consider knowledge as the sum total of known truths and science as equivalent to knowledge. Let us now look at each step: question, hypothesis, experiment and answer individually. The question may arise out of careful observation or careful analysis of existing knowledge. If you have framed your question properly, you are already on your way to finding the answer. A well-framed question is one to answer which means are available within the framework of the method of science. The more carefully you observe, the better framed your question would be. For example, the observation is, many living species have 6 legs. A well-framed question would be, how did these species come to have 6 legs? Do these species have other common features? Could these species have originated in nature from a common ancestor? Does the possession of 6 legs help the insect in any way? Questions such as these led Charles Darwin to frame his famous theory of evolution. The hypothesis should be testable. A testable hypothesis is one which can be tested by an experiment, or on the basis of which testable predictions can be made. For example, the observation is, objects, if left unsupported in space on the earth, will fall to the ground. An untestable hypothesis would be, they fall to the ground because God wills them to do so. A testable hypothesis would be, an object falls to the ground because there exists a force of attraction between the object and the earth. Starting with such a hypothesis, Newton arrived at his well-known law of gravitation. The objective of an experiment should be to either find an answer to a question or to prove or disprove a hypothesis. The experiment must be planned and carried out with care. One should record everything, expected or unexpected, whether you wished it to be so or not. An unexpected observation could lead to an important discovery. For example, in 1928, Fleming made the unexpected observation that there was no growth of bacteria around the area where a mold, which he called penicillium, had accidentally settled on a dish on which the bacteria were growing. He pursued this unexpected observation and discovered penicillin. The answer you arrive at could be a generalization. A generalization, often stated as a law, is derived from a set of experiments which confirms a single hypothesis of general applicability or a group of related hypotheses. For example, albinos totally lack the skin pigment melanin. In another disease, hemophilia, the blood does not clot. The question would be, how are these diseases caused? A testable hypothesis would be that albinism and hemophilia are caused by a genetic biochemical disorder that renders the system incapable of making the skin pigment or clotting the blood. This can be checked by experiments in which we may look for other albinos or hemophilics in the family and determine the biochemical basis of the deficiency. The results of such experiments have established that an enzyme deficiency can cause abnormalities such as albinism or hemophilia, a generalization of considerable importance in medicine. Let us now see how the method of science can be used in different situations. When we wish to find an answer to a specific question, the like of which has been answered many times before, we do not need to frame a hypothesis. For example, question: find out the density of the given liquid at room temperature. Experiment: weigh a known volume of the liquid on a balance. Answer: divide the observed weight by the volume. When we need to find an answer to a question to which the answer is wholly or partially unknown, we need to go through the entire sequence of question, hypothesis, experiment and answer, sometimes several times over. Often we need to find an answer to a question under conditions where an experiment is not possible. For example, the question is, what shall I do to have my brother who is suffering from typhoid get well as quickly as possible? One may then frame various possible hypotheses. In this case, some possible hypotheses would be, I should go to a place of worship and pray for him. I should let nature take its own course and hope for the best. Or, I should give him an extract of certain commonly used spices recommended by a friend. Or, I should seek the advice of a competent doctor trained in medicine. It is obviously not possible to experimentally test all these answers in such cases. Instead, one determines which answer would be most compatible with existing knowledge. In this case, if I were to use the scientific method, I would decide to consult a competent doctor trained in modern medicine. The method of science can be applied in this manner for answering questions pertaining to a vast range of human activity, from decision-making in daily life to ethics, politics, economics, and human behavior. An example of the application of the method of science. Let us look at yet another specific example of the application of the method of science. The question is, what is the path followed by light? The simplest hypothesis would be, light may travel in a straight line. To test this hypothesis, we could do two simple experiments. The first experiment. If light were to travel in a straight line, the light source A should not be visible through hole C when the source A and holes B and C are not in a straight line. And indeed, it is so. The second experiment. The light source A should be visible through the hole C when the source A and holes B and C are in a straight line. This also turns out to be true. The results, therefore, support the hypothesis we made that light travels in a straight line. We can arrive at the same conclusion, that light travels in a straight line, through many other experiments. For example, in the case of the laser beam, one can see the light travelling in a straight line. Therefore, we may now formulate the law that light travels in a straight line. Remember that the above law would be expected to hold true only for the conditions used in our experiments. You would find that the above law breaks down if, for example, a uniform medium was not used for the light to pass. We may therefore also conclude that when stating a law, it is important to define carefully the conditions under which the law may be expected to hold true. At times, light may appear to travel in curved lines, as in the case of fiber optics. Note the light at the tip of each thin, spaghetti-like fiber. It comes from the hidden bulb, following the curvature of the fiber. This phenomenon can be explained in terms of the law we just enunciated. Light from the bulb undergoes a series of total internal reflections and thus appears to follow a curved path. The case is therefore not an exception to the law that light travels in a straight line.
Landmarks in the history of the method of science and its application. At this point, it would be interesting to see how the method of science we have just discussed has developed through the ages. What we would now discuss would not be landmarks in the history of science, but landmarks in the history of the method of science. In fact, many have used the method of science all through the history of mankind without being aware of having done so. Roger Bacon was the first to recognize the importance of experiments and of direct observation. Here is a page from Bacon's notebooks in which he has attempted to describe the phenomenon of eclipses and comets using the scientific method. The famous Mona Lisa was not only the work of the artist Leonardo da Vinci, but also of Da Vinci the scientist, whose contributions led to the beginning of a new age, the Renaissance in Europe. There was hardly an area of knowledge to which he did not contribute. For a long time it was believed that the sun revolved round our earth. Copernicus showed that it was the earth that revolved round the sun. This was the first major scientific discovery that toppled a widely held non-scientific belief. Francis Bacon formulated the first formal statement of the method of science. The making of experiments, the drawing of general conclusions from them, and the testing of these generalizations through further experiments. With Galileo of Galilee in Italy began the breach between science and religion. He was the first outstanding scientist to be victimized by religious leaders because of the views he held. Galileo supported Copernicus and died under house arrest. Galileo was the first to use the telescope for examining extraterrestrial objects. He also discovered the pendulum. Descartes introduced the rigid concept of mathematics and logic and of the method of doubt and questioning into the method of science. His celebrated 4 rules of logic are the best recipe that one has even today to find an answer to a problem or to arrive at an opinion which will stand the test of time. Isaac Newton was the first to apply the experimental method, the method of science, for arriving at a set of interrelated generalizations. His books, Philosophiae Naturalis and Optics, revolutionized physics. The founding of the Royal Society in Britain in 1662 and the Académie Royale des Sciences in France in 1666 made organizational support available for the first time to the idea of conducting experiments. In the 1780s, the method of science began to be used for the first time for organized and efficient industrial production. The Industrial Revolution began through a large-scale establishment of factories. Using the method of science, Friedrich Wöhler demonstrated that substances such as urea made by living systems are not anything special and can be made in the laboratory from non-living materials. With Charles Darwin came the first major application of the method of science in the synthesis body of descriptive information, which led to the theory of evolution and the idea that man has evolved gradually from lower forms of life. This theory led to a major confrontation with religion. Darwin's revolutionary concepts generated not only controversy but also much humor. Louis Pasteur laid the foundation of modern biology by demonstrating that living organisms can be generated only from similar living organisms. He also recognized the role of bacteria in spoilage of food and disease. Karl Marx and Friedrich Engels were the first to apply the method of science to the study of human history and to an integrated analysis of social, political, and economic problems. This analysis led to the formulation of the first science-based socio-politico-economic theory. Hopkins' discovery of vitamins laid the foundations of the science of nutrition, which tells us what to eat and how much to eat. Hopkins won a Nobel Prize, and later on so did 7 of his collaborators, one after the other. Lenin used the scientific method to formulate the concept of planning for development and for achievement of social objectives. With Einstein began the age of the grand generalizations in physics, one of the best known of which is the theory of relativity. Bernal, a renowned physicist, made the first formal statement of the intimate relationship between science and society. Blackett and Bernal were together responsible for the first highly successful application of the method of science to the conduct of major operations in a war, World War II. They worked out the ways and means of combating the U-boat menace during the war. This is how operational research came into being. Blackett won the Nobel Prize for Physics in 1945. 1942 saw the beginning of the nuclear age, with Fermi's achievement of the first controlled nuclear chain reaction on the tennis courts of the University of Chicago in the United States. The many uses of nuclear energy for peaceful purposes, for example in the cure of cancer, have transformed our lives. It is a pity that the specter of a nuclear war continues to haunt us. Francis Crick and James Watson determined the structure of the genetic material in 1953. With this discovery began the modern biological revolution. the landing of Neil Armstrong on the moon and his return to Earth in 1969 was the most spectacular demonstration of the fact that science allows one to make testable predictions.
How does science progress? In science, an existing answer gives way to a new answer when new experimental evidence is obtained which is not in conformity with the existing answer. The new answer satisfactorily explains all observations that were explained by the earlier answer, plus some additional observations not explained by the earlier answer. Predictions can be made on the basis of the new answer, which could not have been made on the basis of the earlier answer. Some of these predictions have been tested, and every prediction tested has turned out to be right. Let us now look at an example of progress in science that pertains to the motion of objects and properties of light. In the 17th century, Isaac Newton formulated his famous laws of motion and gravitation. In the first half of this century, Albert Einstein formulated his famous theory of relativity, which explains all that was explained by Newton's laws, plus many observations that could not be explained by Newton's laws. For example, Newtonian physics cannot explain the observation that black holes exist in space into which light may enter, but from which it will not come out, or that the mass of an object depends on its speed, or that mass and energy are interconvertible, or that light bends in the presence of a large gravitational force such as that of the sun, or that the wavelength of light increases as a result of its passage close to a massive object such as a star. Therefore, Einstein's theory of relativity evolved from and modified Newton's laws. Another example illustrating how science progresses pertains to the structure of matter. In the 19th century, John Dalton formulated his famous atomic theory, according to which the atom was considered indivisible. In the current concepts of the structure of matter, an atom is a complex structure consisting of electrons going round a nucleus. These concepts evolved from Dalton's atomic theory and explain many phenomena or observations that cannot be explained by the earlier theory, such as water, a non-conductor of electricity, becomes a conductor when salt is dissolved in it, or that many substances carry an electric charge, or that different elements may exist in forms which have the same atomic weight, or that certain elements are radioactive but others are not. An important attribute of science is the right to question. Knowledge advances and science progresses because people exercise their right to question. For example, in the 15th century, Copernicus questioned the age-old belief that our Earth was the center of the universe and that the sun or the planets revolved around it. He used the method of science and his creative ability to show that his doubt was justified and the age-old belief was unfounded. Here is another example of addition to knowledge through questioning. For centuries, it was believed, and many people still believe, that there is only one point on the surface of the earth from where, if you travel 1 mile south, then 1 mile east or west, and finally 1 mile north, you would reach where you started from. This point is obviously the North Pole. We now know that there is an infinite number of points lying on a series of loci from where one could do the same thing. Science has no high priests who cannot be questioned. No scientist can insist that whatever he says must be accepted without questioning, that is, entirely on the basis of faith in him. There has probably never been a scientist who has not been questioned and shown to be wrong some time or other. Science, therefore, does not accept the existence of God-men who have special powers that cannot be understood by other men, and whose statements and actions must, therefore, be accepted by others without questioning.
New discoveries in science often disprove a part or whole of an existing scientific belief. Let us look at some examples. Estimates in the past of such a simple parameter as the density of air have differed very significantly from the value accepted today. Estimates of the daily protein requirements of the adult male have also changed drastically over the years. At least 2 Nobel Prizes were awarded for discoveries which were later partially disproven. In 1927 to Heinrich Wieland for discovering the structure of cholic acid, which was eventually proved wrong, and in 1959 to Ochoa and Kornberg for the discovery of enzymes which carry out the synthesis of substances responsible for heredity in living systems, which turned out to be the wrong enzymes. In 1962, George Sudarshan, an Indian scientist, showed that faster-than-light particles called tachyons may exist. This would seem to go against the fundamental law that nothing can travel faster than light. Till recently, it was widely believed that the major nutritional problem in the developing countries was the problem of protein deficiency. Recent work has shown that the major problem is that there is just not enough food for the people. It is important to recognize that in every case, the new discovery would probably have not been made if the earlier answer had not existed. The answers in science, that is, the facts and the generalizations, are truths by agreement of opinion based on the method of science. The agreement has to be reached among people who have formed their opinion by using the method of science. As time passes, the chances that the initial agreement of opinion will prove to be wrong diminish. This is the test of time in science. For example, the chances that the known composition and structure of water will be proved wrong in the future are extremely remote. On the other hand, there is yet no known theory of cancer which has stood the test of time. It follows that an important objective of scientific training should be to enable one to evaluate evidence against an existing scientific answer. Science does not claim to provide immediate answers to every question that can be asked at any given time. A scientist can say, without any feeling of guilt or shame, "I don't know." For example, we don't yet know how the universe arose, what the mechanism of memory is, that is, how our brain stores, puts together, and recalls information, and what the ultimate fundamental particles are of which all matter in the universe is composed. What science considers undesirable is not the lack of knowledge, but the lack of curiosity and of the desire to learn. What goes entirely against science is the acceptance of answers that are incompatible with knowledge acquired through the method of science. For example, there are some widely used systems of medicine which are not compatible with the method of science. Similarly, doctors very often prescribe glucose for oral consumption when science tells us that ordinary sugar, that is cane sugar, which is much less expensive, will do just as well.
Science does not seek an explanation of the unknown in terms of another unknown. If he finds that no scientific answer exists, he uses the method of science to obtain the answer. Science denies the existence of the supernatural and magic. One often witnesses or hears about events which, in the opinion of many people, can have only a supernatural explanation. That is, an explanation outside the scope of the method of science. In reality, all such events do have a scientific explanation, often simple and ingenious. For example, the famous magician Houdini could swim ashore safely after he had been tied in a sack, the sack placed in a trunk, the trunk locked and then dropped in a river bed. He could do this because he swallowed a knife and the key to the trunk just before he was tied up, and he had developed the physical ability of vomiting them out at will. Here is a live magic show. Don't you wish all inanimate objects could obey your orders as this ball in the exhibition does? And it would certainly be fun if you could light a tube light or have a rag catch fire with a touch of your finger. The performer, however, does not claim any supernatural powers. He says these are only tricks and nothing more. In other words, there is a scientific explanation for what he does. Observe carefully and see if you can guess. Therefore, we conclude that if someone produces a rabbit out of a hat or a watch out of nowhere, he is performing a trick. All magic is tricks with relatively simple scientific explanations. Science is not dogmatic or unreasonably insistent. Science does not ask you to accept anything on faith. Science does not regard truth as unchangeable or unmodifiable. Scientific observations are verifiable and repeatable. Here's an example. If we mix specified volumes of solution A and solution B, the mixture will turn violet from colorless. And it will take exactly the same time to do so, irrespective of who does the mixing, what you may personally like to happen, the place where the experiment is done. It would of course be necessary to ensure that the experimental conditions are maintained constant. This is a time reaction which can be used as a chemical clock. Science is forward-looking. Those who believe in science, unlike those who believe in dogma, desire the latest in knowledge and techniques and are concerned more with the present and the future than with the past. Science possesses no articles of faith. Science has no prejudices. Science is not orthodox. Science is not conservative.